Welcome back. This video lecture would focus on the input and output characteristics of a common base configuration. The presentation outline or the learning objectives of this video lecture would be to outline the different configurations of BJT, explain what is the input characteristic of a bipolar junction transistor, explain what is an output characteristics of a BJT, explain what a common base configuration is all about, and also outline the input and output characteristics of this particular common base configuration. When we were talking about configuration, we understood that either the emitter can be had as a common terminal, or the base can be had as a common terminal, or the collector can be had as a common terminal. So based on that, you do have three different types of configuration. The first one is called as common base configuration, the second is common emitter configuration, and the third is the common collector configuration. As the name implies, common base, the base is kept as the common terminal. In common emitter configuration, the emitter is kept as the common terminal, and in the common collector configuration, you do have the collector to be the common terminal for both the input and the output terminals. You have it as base and you can have this as emitter. So this is how the arrangements are. Having known these prerequisites, we will dive into common base configuration and we will try to understand the input characteristics and output characteristics of a common base configuration. So this is going to be the arrangement in a common base configuration where the base is kept as the common terminal. So we have taken an NPN transistor. The input is applied across the emitter base terminals and the output is taken from the collector base terminals. So this is another picture which illustrates the common base configuration. Base is the common terminal. You forward bias your input and reverse bias your output. We are in the forward active mode. Input is forward biased and the output is reverse biased. So this input is applied across the emitter base and the output is taken across the collector base. Now we will understand what a current gain is. Normally, what is gain? You have 5 chocolates in your hand and by some magic you have got 10 chocolates in your hand now by some magic. And what is the gain? The gain is 2, is it not? And how do you obtain this? You obtain this by dividing your output by your input. Output by input. So this is what is called as chocolate gain. 5 chocolates, out of magic you have 10 chocolates in your hand. Now the chocolate gain is 2. You have chocolate gain now. If you want voltage gain, you will divide output voltage by input voltage. Now we will try to get what a current gain is. Current gain is output current divided by input current. And for a common base configuration, the output current is your collector current and your input current is your emitter current. And how do you write the equation now? The equation now is written as IC by IE and the current gain of a common base configuration is given by alpha. So alpha is equal to IC by IE. This is a very important expression that we will have it in our mind. We will move on to the setup or arrangement of the circuit. This is a setup PNP transistor. Conventionally, we do an NPN transistor. The arrangement goes like this. This is the DC supply that we give, the input voltage that we measure, the output voltage that we measure through this voltmeter. Ammeters are used to measure the currents that are going to flow in your circuit. This is an NPN transistor. Now we will try to understand the procedure first. Now what do? We do change the input voltage and measure the voltage across this emitter and base. The base is the common terminal here. So we change the input voltage and measure the voltage in this voltmeter and we measure or note down the corresponding current here. So the input voltage is VEB and the input current is your emitter current. And what are we going to do to understand the input characteristics? We change the input voltage and we note down the corresponding input current, keeping this output voltage constant. Okay. Now we change this voltage, say for example you change this voltage, and if the readings in the voltmeter says 1 volt, you should not disturb this supply thereafter, right? So for 1 volt, the output voltage 1 volt, we will understand the input characteristics. Keeping this output voltage 1 volt constant, we will start changing this input voltage here. And by changing the input voltage, we will note down the corresponding current in this ammeter. And that is how you draw the input characteristics. So the input voltage is VEB, the voltage across this emitter base terminals, and the input current is the emitter current flowing through this ammeter. Now, what really happens? I am at 0. Now I change this and see that the reading is 0.1 here. Okay? And what will be the current? The current will be 0, because when will you have a considerable flow of current, emitter current in your circuit? When VEB is greater than 0.7. Only then you will have an appreciable amount of current flowing in the circuit. This we have already known. Fine. So 0.1, there will not be any current. So the current is going to be 0. When it is 0.2, the output voltage is VCB. Okay. When it is 0.2, still there is not going to be current. For 0.3, 0.4, 0.5 and 0.6, no, you will not have any current. When the voltage reads 0.7, the forward bias, the depletion region shrinks, right? And as a result, the electrons will move from the emitter to the base. This is what is going to happen, right? Once it reaches 0.7, right? So there is going to be a flow of emitter current, right? So the electrons will start moving through the depletion region, because the depletion region would have shrunk, and it would pave a way for the electrons to move from the emitter to the base. And as a result, you will have a flow of current, which is your emitter current. So this is for the collector base voltage at 0 volts. Now I need to have, now this is one set of a reading. I need to go for another set of reading. I need to take multiple readings. I will change this output voltage here for the second set of reading. Now I am changing it, and say for example I can keep it at 1 volt, or I can keep it at 2 volts or 3 volts, and so on and so forth. It's your choice. It's our choice. Now for example, I do keep it at 2 volts. Then I need to repeat the same procedure. After that, I can keep it at 3 volts or 5 volts or 10 volts. I will do the experiment one more time. I will experiment and take another set of reading. So you will have graphs. Now the question is, when I keep it at 2 volts or 3 volts or 10 volts, now what would happen to the curve? Will the curve move upwards? Say for example, so this is the first set of reading I have, right? I'm going for a second reading. My question is, now what would happen to this second set of curve? Will it move upwards, or will it move on the downward side, or rather will the curve move on to the downward side of this 0 volts? We will try to understand now. Good. Now we have increased this collector base voltage, and what would happen? This is a reverse bias. When the reverse bias increases, the depletion region will widen, and though the depletion region widens, it is easy for the minority carriers to move across this depletion region. We have already understood the concept. For majority carriers, it is like climbing a hill, and for minority carriers, it is coming down the slide. The minority carriers inside the collector is your holes, and when you increase the reverse bias, the minority carriers, the holes are pushed. No, it is like forward biasing for holes. It is reverse biasing for the majority carriers. For the minority carriers, it is forward. It is like forward biasing, and so they are pushed towards this base region. And from here, the holes will move to the emitter region, because the negative polarity would start attracting the holes to the emitter. Already there would be an emitter current that would be flowing. So electrons will move in this direction. The conventional flow is in this direction, which is very much the same as that of the hole current, is it not? The hole that has come from the base will have the direction in this way. So there is an additional current because of the holes that move from your emitter towards your negative polarity of the input DC supply. We will understand this concept by taking numerical values. First, let us take VEB to be 0.5 volts and VCE equal to 0 volts. This is for the first set of reading. When VCE is going to be 0 volts, already there is a current because of electrons, which is nothing but the emitter current, which is having a magnitude of 10 milliamperes. As VCE is going to be 0 volts, take for example, there are no holes traveling from the collector to the emitter, and so it is going to be 0. So the total current is the emitter current plus the hole current. So the total is 10, right? And for 0.5 volts, now this is for the first set of reading when VCE is equal to 0 volts, which we had drawn earlier, 0 volts, right? So 0.5, the value of current is going to be 10. Say for example, now this is going to be 10. So you mark it here. We will take the second set when VCE has increased to 2 volts. I have increased this VCB to 2 volts. Now VCB, I'm sorry, this is VCB and not VCE. VCB to 2 volts, right? I have not changed this. I should not change this, right? So 0.5. Right? So because I'm taking this reading, for this reading I'm trying to find out whether it is moving upwards or downwards. I keep it at 0.5 for 0.5 and for 2 volts, right? Because of this 0.5, emitter current is going to be 10, and due to this 2 volt supply, I have 10 holes coming inside the emitter. So already there is 10. Now I have additional 10. So altogether, the magnitude of my emitter current increases to 20. Fine, which means that 0.5, it was 10, now it is 20, right? So the curve would have gone like this for the first set of reading, and the curve would go, it would come here and it would come like this. So the curve will shift upwards. This is for 0 volts and this is for 2 volts, and the curve now shifts upward. Say for example, if you change this and keep it at 5 volts and do the experiment, the curve would still move upwards and the curve would be like this, 5 volts, and that is shown in the graph here. So this is VEB, this is your input current IE, keeping your output voltage constant, right? And the curve is here, right? So this is for 0 volts and now this is for 1 volt. In case if you perform the experiment for 5 volts, the graph will still shift upwards. This is the input characteristics of a common base configuration. We have come to know that the curves shift upwards in the input characteristics of a common base configuration. Now we'll find the reason for it. The shifting of the curve upwards in the input characteristics of a common base configuration is due to a phenomenon called as base width modulation, otherwise called as early effects. Are the regions of a bipolar junction transistor. As we forward bias the emitter base junction, you do have a smaller depletion region, or rather the depletion region of the emitter base junction shrinks. When you reverse bias your collector base junction, if this is taken as a NPN transistor and you reverse bias it, now what would happen? There is already a depletion layer formed. Now because of the reverse bias, the depletion region widens. As the base has a lighter doping, the extension of the depletion region inside the base increases, right? If the depletion region had been here already, now increase in the collector base voltage, the depletion region extends deeper inside the base. Now the extension, or rather the width of the depletion region has widened, and so the effective width of the base is lessened. This phenomenon is called as base width modulation or early effect. Now, why do we call it as modulation, base width modulation? The variation of the effective base width by the collector voltage is known as base width modulation. What you do is you change the or vary the effective base width by changing the collector voltage. You modulate the effective base width by changing the collector voltage, and this is what is called as base width modulation or early effect. And what are the consequences of this base width modulation? The first consequence is alpha increases, the common base current gain increases. We already know that alpha is equal to IC by IE. So the base is normally made thinner, and due to this reverse bias, reverse collector base voltage, the depletion layer extends deeper inside the base and the effective width of the base is reduced. So the electrons coming or flowing from the emitter do not find enough holes in the base to recombine. So almost all the electrons that come into the base move to the collector, and as a result the collector current increases. So the numerator increases here, and so alpha increases. So this is the first consequence of the phenomenon. The second consequence is the concentration gradient of minority carriers increases. We know that when a reverse bias is given to the collector base terminals, this reverse bias becomes a forward bias to the holes or rather the minority carriers that are present in the collector, and as a result these holes, because of this collector base voltage, they are pushed towards the base region, and as a result the concentration gradient of minority carriers will increase. So this is the second consequence. And the third consequence is another important phenomenon called as punch through. Now what is going to happen when you keep on increasing your collector base voltage? Yes, the depletion region will extend deeper and deeper inside the base, and at one final voltage what would happen is both the emitter and the collector touch each other, become a short, and so the current increases dramatically and the transistor reaction is lost eventually, and this phenomenon is called as punch through. Now what is the importance of this input characteristics? We will be able to find out the input resistance of the common base configuration from the input characteristic. The AC resistance, the AC input resistance could be determined, which is given by input resistance is equal to change in your emitter base voltage to the change in your emitter current. You could notice that for a small change in your emitter base voltage, there is a good amount of change in the emitter current, and so the denominator is comparatively higher than that of your numerator, and as a result we could say that the input resistance of a common base configuration is less. So this is what you could determine from the input characteristics of a common base configuration. Now we will understand the output characteristics of the NPN bipolar junction transistor. The experimental setup is the same, but the procedure varies. First we will outline the procedure. We change the output voltage, and for every change in the output voltage we try to note down the corresponding output current. And how do we do that? By keeping the input current to be constant. First we need to set up a fixed emitter current. For that we change the input supply and set up a current in the input side, which is nothing but the emitter current. Say you can fix it at 2 milliamperes. Now once you change this, now you will have a input current that is going to flow. right? So that is what we had seen. Once you set this current, you're not supposed to change this voltage because we need it for a fixed current. Now, keeping this as constant, keeping this input emitter current to be constant, we start changing this supply. Once you change this supply, now you will have changes in your collector base voltage. For every change in your collector base voltage, you note down the corresponding collector current and you obtain a graph. Say, for example, you do obtain a graph like this for a fixed emitter current, say 2 milliamperes. And what are we supposed to do next? So this is a curve that you have got, one curve that you have got. You need to have different curves for different emitter currents. Is it not? Right? So what you need to do is, in order to obtain the second set of readings, now I need to change this emitter current and keep it fixed thereafter, right? So for that, what I will do is, I will, for the second time, I change this voltage and say I keep the emitter current to be 4 milliamperes, and keeping this as constant, I repeat the procedure at the output side and I will have a second curve here. So this is how I will obtain the output characteristics of the NPN bipolar junction transistor. One set of curve, and then we will analyze the output characteristics in detail. Now we have three regions in a bipolar junction transistor: emitter, base, collector. This is N type, this is P type, and this is N type. For clarity, we have taken an NPN transistor. So this is the origin, and to the left side of the origin we do have negative voltages. On to the right we do have positive voltages, right? On to the y-axis, above this you have positive current, the direction of current, right? And this you have the direction of current in the opposite direction when it flows in the y-axis below this origin, right? So this is VCB, which is measured in volts, and this is IC, that is measured in milliamperes. The collector current measured in milliamperes. First, we will try to get what happens when you give the collector base voltage to be negative, right? When you say VCB is equal to minus 1 volt, it means that the collector is more negative than the base. I repeat, VCB equal to minus 1 volt, it means that the collector is more negative than the base by 1 volt, right? So what happens? This is like biasing the collector base in this fashion. This is negative and this is positive. Normally the collector base junction has to be reverse biased, but when you give the collector base voltage to be a negative value or negative quantity, right? It is like biasing in this fashion. What is the kind of biasing that we have done now? It is forward biasing, right? So when you give a collector base voltage to be a negative value, it is like forward biasing your collector base junction, right? And as a result, now what would happen? The electrons flow in this direction. Normally when you reverse bias your collector base junctions, the electrons flow in this direction, but now the direction of electron flow is in the opposite direction, right? And so the conventional flow of your collector current would be out of the terminal rather than into the terminal, and so your current is from here, okay? It is in the opposite direction, right? And as and when you start increasing from minus 1 volt, right, minus 1 volt to say now minus 0.9 volt, minus 0.8 volt, and minus 0.7 volt, and so on and so forth, right? If you start increasing, so this would be moving towards reverse biasing, right? Forward biasing would start becoming reverse biasing, right? So this would be a much, say for example, if you give minus 0.9 volt, would be more positive than this, more positive than this. If it is minus 0.5 volt, this volt is more positive than this. So automatically when it is more positive and the collector is more positive than the previous value, it is like reverse biasing your collector base junction, and so automatically the current starts flowing in this way, right? So opposite to the direction of current here. So it is flowing here, right? And at one point, say VCB equal to 0 volt, the emitter current starts flowing, right? This we had already seen in input characteristics, right? Even if you don't give any collector base voltage, when collector base voltage is going to be 0, you will have the electrons from the emitter flowing into the base, and due to this barrier potential, due to this voltage developed across this depletion region, this electrons will be pulled to the collector region. Fine, right? And so automatically, so there is a current that is going to flow, right? Even at VCB equal to 0 volts, right? And this is what we call it as a collector current, right? So the emitter current, so the electrons in the emitter start flowing into the collector, right? Even at VCB equal to 0 volts. And from thereafter, right? Even if you increase your collector base voltage, right, thereafter when you increase your collector base voltage, right, so the we had already seen the concept of punch through, right? So the depletion region starts widening. That will not stop the electrons from the emitter flowing into the collector, right? That will not stop, right? And the electrons would start flowing because the electrons, they become minority carriers when they come to the base, and it becomes very easy for the minority carriers to cross the depletion region and come to the collector region, right? So that these concepts that we have already seen. Okay, so and so automatically, so if there are 10 electrons that are going to be present when you set up the fixed emitter current, so these 10 electrons would start flowing inside, right? And even if you increase your collector base voltage, that will not have any effect on the number of electrons coming inside, right? If there are 10 electrons, these 10 electrons would start coming into the collector at a constant. Now that is going to be fixed. So you will have a flat curve, right? And we had again, it is for us to recollect that when you start increasing your collector base voltage, the depletion region widens deeper into the base, and at one point of time it touches this emitter region, the depletion region of emitter region, and so the emitter shorts with the collector, right? It becomes a short circuit, it becomes like a short circuit, and once you have a short circuit, there is going to be a sudden increase in the current, right? So the transistor would lose its normal behavior, it breaks down, and there is going to be a increase in the current. So this point, this is the voltage at which the transistor loses its property, it breaks down, and the current increases dramatically. So this is for a fixed emitter current, say 2 milliamperes. Fine, right? So now we will try to understand the different regions in detail, right? So first we will try to get this region, right? So this is a region where both the emitter base junction and the collector base junction are forward biased. You could notice, right? So when it is given a -1 volt, now we say that it is forward biased. When both the junctions are forward biased, we already know that the transistor is working under saturation mode. And once you come to this region, right, this region, what happens to this bias? This bias becomes a reverse bias. Now the input is forward biased, and the output is reverse biased, which means that this is the active region. And there is one more region which we call it as the cutoff region, and we will discuss about that in our next slide. Hope you understand this concept. Fine. So this is the set of curves that we obtain for different values of the emitter current. You could notice this is the direction of current initially, and when you start increasing your collector base voltage. To put it in other terms, when you make the collector base voltage more positive than the other, you could see that the direction of current changes, and for a small change in your collector base voltage, there is a dramatic increase in your collector current. Okay, and so up to this region you will have a increase in your current, and after reaching this point, right, a borderline where VCB is equal to 0 volts, so there is going to be steady flow of electrons from the emitter to the collector, because we have kept the emitter current to be fixed, right? If it is 2 milliamperes, say only 2 electrons are going to be generated in emitter, so those 2 electrons would be would flow from the emitter to the collector, right? And so you will have a constant flow of current, and that is why you have it over here, right? A constant flow of current. And so the breakdown is not shown here, right? So once a particular voltage is reached at which punch through happens, you have a breakdown, and there is going to be a sudden increase in your current. Fine, right? So this is a point. This is another parameter of concern. When the emitter current is going to be 0, right? Still there is some amount of current that is going to flow. Understood, right? So there is an amount of current that is going to flow still by even when your emitter current is going to be 0, right? And this is because of the minority carrier flowing from the collector region, right? So VCB is reverse bias. So this is how it is: emitter, base, and collector. Okay, right. So this is IE is equal to 0, which means that you have open circuited, right? You have not connected any supply. You're open circuited, but you have reverse bias your output terminals, right? So what happens? So there is going to be holes which are minority carriers, and these holes are going to be pushed from here to here, and from here it is going to be pushed here, right? And so there is going to be some amount of current that is going to flow because of the minority carriers, and that is this line below which the region below which is called as cutoff region, where you do not have any current flowing in the transistor. So there are 3 regions. One is the saturation region, the next is the active region, and the cutoff region, where the current is going to be very it's almost nil, but there is going to be some amount of current that is going to flow because of minority carriers. So this is the output characteristics of the bipolar junction transistor. One point to know: IC is almost equal to IE. When IE is equal to 2 milliamperes, IC is also 2 milliamperes. When IE is equal to 5 milliamperes, IC is also equal to 5 milliamperes, right? We will try to understand the reason for it, right? As said earlier, emitter, base, and collector. So this is going to be reverse bias, and this is going to be forward biased. Once you set this bias, right, say 5 milliamperes, and there are going to be 5 electrons present inside. No, they're generated here, so there are going to be 5 electrons here. So 5 milliamperes you have set, and 5 electrons are going to be there. No, this is for understanding, right? Say for example, and what you do is you start from here. You start from here. So gradually there is going to be as you make the collector base voltage more positive, right? So there is going to be a gradual increase in your current, gradual increase in your collector current, right? And when VCB equal to 0 volts, right? When VCB equal to 0 volts, so this is like forward biasing, right? So this is now reverse bias. When VCB equal to 0 volts, now you don't give any voltage, but after this becomes reverse bias. Fine, right? So when it is reverse bias, whatever because this is going to be fixed, whatever electrons that are going to be present, so this is going to generate 5 electrons at a time. So these 5 electrons will come to the base and they jump to the collector, right? So the generation is going to be 5 electrons, the reception is going to be 5 electrons. When you make this as 15 milliamperes, there are going to be 15 electrons that are going to be generated at a time, and so these 15 electrons are going to be pushed to the collector, and so you will have this occurrence, right? When IE is equal to 2 milliamperes, you will have collector current to be 2 milliamperes. When you have IE equal to 5 milliamperes, you have collector current to be 5 milliamperes, right? So this is one way of understanding, right? The other way of understanding this concept is through this equation, through this mathematical expression. We already know that we have understood the current components of a transistor, right? Majority carriers, because of majority carriers, right? IE is equal to IC plus IB. IE is usually measured in milliamperes, IC measured in milliamperes, and base current is measured in microamperes because the current, the base is very thinner, the number of holes that are going to be present is going to be very less. Recombination happens with the available number of holes, right? So as the holes are going to be very less, the current that is going to be generated, the base current is also going to be very less, and that is going to be measured in microamperes, right? And when you just ignore this base current as it is in microamperes, right? So IE approximately equals IC, and that is why we do have a graph like this. Okay, right? So we have already seen this saturation region, about the saturation region at VCB equal to minus or rather negative voltage. This is a region and VCB equal to 0 volts, right? So this we have already seen. Even at VCB equal to 0 volts, you have emitter current flowing, right? So emitter current. Now emitter current is approximately equal to IC, and so automatically, so this we have understood already, right? Even when the collector base voltage is going to be 0, so these electrons are going to be pushed inside the base, and it is going to be drawn towards the collector, right? And so you have collector current flowing even when VCB equal to 0, right? At the active region, so the collector current is independent of the collector base voltage. Though you change the collector base voltage, you don't have any change in your collector current. Okay, so it is going to be constant throughout. Fine. And the effect of collector base voltage happens when punch through. We found out the input resistance, the AC resistance using input characteristics. Using the output characteristics, we can find out the AC output resistance of a common base configuration. Output resistance of a common base configuration. Resistance RO is given by, R is equal to V by I. Change in your collector base voltage to change in your collector current. Output resistance will involve output parameters, right? So the output parameters are the collector base voltage and the collector current, right? So when you see here for a particular graph, right, for a particular set of readings, say IE equal to 4 milliamperes, right? So when you see a change in your collector base voltage, right, 6 and 8, so it is going to be 2, right? And what is the change in your collector current? You don't find any change here, right? In case if you have a graph like this, you can find out a change in your collector current. As the collector current is going to be constant here, you cannot get the change in your collector current, and so it becomes 0, right? So R naught is equal to del VCB by 0, which is equal to infinity, and so we say that the output resistance of the common base configuration is going to be very high. The input resistance of common base configuration is less. The output resistance of the common base configuration is going to be very high.
We had discussed comprehensively the input and output characteristics of the bipolar junction transistor. If you really like the video, please press the like button, post your comments, and forget not to subscribe to this channel. Thanks for watching the video. We will meet again in yet another interesting video lecture.